It'll be focused on Nastran and Marc's contact. Where they differ, I'll try and explain that. The first session is just going to be an introduction to the basics. Okay, so what we'll cover in this series over this couple of weeks, months and so on, is we'll start with contact algorithms, what they are and why we need them. The basics of contact in Nastran and Marc, things you should absolutely know before you can even start. We look at the contact table or contact body pairs. Contact table is only in, this is in Marc and Nastran. The contact body pair is only in Nastran. They're trying to do the same thing though. Then we've got multi-segment algorithm, which is the older, really well established algorithm for contact in Marc and Nastran. It's really capable. There's some specific things it doesn't do as well as the newer one, the segment to segment, which has got other problems again. I'll explain all of those once we get there. And then we'll have some special topics like interference fits, friction models in Marc, and so on. Okay, so in this session, we'll only look at the first two, the contact algorithms, what it is and why it's needed, and then the basics of contact in Nastran and Marc. It's not going to be a very long session. I'll estimate somewhere around half an hour. If there's any questions, please don't hesitate to ask. If we have a mesh, then information is transferred from one element to the next only through nodes. So in other words, if I apply a load to that node and moves in some way, both of these elements will distort, and due to that distortion, effectively there's a strain generated, and that translates into stress. So only at nodes can information be transferred from one to another one. Okay, so elements are always connected when they share nodes. In other words, there's no possibility of it separating in any way, so contact isn't quite possible with the standard, the classical finite element method. So this is typical of parts that's welded together, signal materials, and so on. So this is just an example. I take that node and I move it, and as you can see, both of these elements change the shape. So that node effectively immediately change the behavior of those. That'll indirectly, if I apply a load there, will obviously transfer to loads everywhere and the whole structure will deform. Okay, but we often have something like this where meshes don't tie up. This is a really, really simple example. In general, we have much more complex stuff, welded, bolted, different parts that come into contact and so on. In this case, there's no transfer of load from that node on the red to the green part because they don't share a node. There's no information that can be transferred if we do not use a contact algorithm. So the purpose of the contact algorithm is to get the nodes on the one body's faces, the outside faces, to touch in some way the faces on the other side. Okay, so the purpose of the contact algorithm then is to manage across these discontinuous meshes a couple of things. Penetration, so in other words, even though it penetrates, it should there's no penetration allowed. So in some way, it should force it so that it doesn't penetrate. I know there's some methods that use a stiffness-based one, so there's a little bit of penetration in that case, but the higher that stiffness, the less the penetration. Okay, then for separation, no tensile forces are allowed. If I want to lift up the red part, then that node should be released again. So moving in, initially, if it's far away, nothing, and then suddenly it adds these equations or whatever is needed to stop it from penetrating. But the moment I try to lift up, it should release that again. Okay, and then we also need to manage friction in a contact algorithm. So the transition between sticking and slipping. So while it's sticking, that node, argument's sake, in contact is not allowed to move sideways relative to the face position where it started at. Okay, so up to sticking ending, in other words, transitioning from stick to slip, that is a constraint effectively between that node and the nose on that face. So sorry, as I said, there's no relative sliding motion, but the moment you exceed that friction coefficient multiplied by the normal force as a friction load, then it transitions from stick to slip. And then we get to that classical equation that says the friction force is the normal force multiplied by the friction coefficient. Before that, it's simply sticking. That friction force times also friction coefficient multiplied by the normal force is a limit for this. It cannot exceed that value initially when it's sticking. But the moment it transitions to slip, and then it starts moving. Okay, so that force in the slipping condition, it changed from a constraint to a force, and that force is now based on the normal force, the friction coefficient, and the relative velocity of the direction. In other words, if that node relative to that phase is moving in this direction, then the force on the red part is to the right. So not the magnitude or the, I just need to look at that sliding velocity, and it's in the 180 degrees opposite to the direction that it's sliding in, is where the friction force is being applied. Okay, then if you look at contact, how do I define what can make contact to something else? In Marc, we define that by using a contact body. Sorry, when I say Marc, it's Marc and Nastran both. So we can define three basic types of contact body. A mesh as a contact body, geometry, which is a surface or a curve, depending on whether it's a three-dimensional analysis or a planar axisymmetry or plane stress, plane strain analysis. And the last one is a symmetry type. So I've got all three of those in this model. So in this case, this is a mesh, a single body. Then I've got a rigid body over there and a rigid body there. Those are the geometric ones. In other words, it's a surface. They've closed it with caps, possibly. Don't really need it, to be honest. But there, in theory, I could have used either just as one, or I could have used three faces. In other words, the cylindrical and the two circular faces. Another contact body over there. Now, this kind of model will now allow me to, if that wasn't there, to rotate about this, and this one to rotate about that section over there. Okay, now, in terms of what can make contact is, we always make contact at nodes, because that's how we transfer information to a mesh. So that means a mesh can touch other meshes. In other words, this node can touch a face somewhere over there, for argument's sake. But we can also touch geometric surfaces, in other words, or symmetry. Now, this is an example of symmetry planes where we create a contact body and we call it a symmetry kind of a contact body. And it automatically applies the correct symmetry constraints to all the nodes that touch on that face. That's really convenient if I've got a weird orientation for my symmetry plane. If it's perfectly aligned with X or the Y or the Z of the global coordinate system, is really easy. But the moment it's rotated in any weird way, in that case, it's simply easier to do it like this. You don't need to, you can still apply the constraints manually, it's just a bit more work to do. Okay, so we'll always have a mesh touching one of the other ones. Now, here's just some more examples. It's shown in wireframe now, but there's also some rigid, so that these are not symmetry. It's used to load this part with. So this was a kind of forming operation. Okay, now in terms of contact bodies, if I have, this is an example, just a meshed part, it looks like there's only one contact body, and this is how they've selected it, I agree. But a contact body, the only purpose of a contact body from a mesh perspective is to find which elements participate in that possible contact. What the algorithm will do is it will say all of these elements are selected. Now let's find the outside faces, because that's the only location where it can make contact. So it will find everything that you see in there, and if we hide those two, you'll also see that those inside faces are selected. But none of these elements towards the inside there can make contact. It's only the outside faces. So that's the purpose of a contact body. Now, more general term would probably have been contact list of elements or something. Contact body just rolls much smoother off the tongue. But there's no requirement that says this need to be one contact body. I can split this into one, another, and I can either make that another contact body or leave it as is. It doesn't really matter. In addition, it doesn't mean that meshes need to be connected to form part of one contact body. An example would be if I have 100 bolts in my model, I can make all of those bolts one contact body. So at first glance, no, it's not a body. as I say, contact group of elements would probably make a bit more sense. But think of it this way, every one of those elements, Marc or Nastran simply finds the outside faces to determine which nodes and faces can make contact. So that's it. So a contact body, as we define it, is simply a convenient grouping of elements that can make contact to something else. The reason we don't make everything in the model one contact body is typically because I want slightly different settings in different regions between different contact bodies. Okay, so that's contact bodies. Now, complications with contact bodies is, let's say I've got a mesh. This is the surface. I haven't meshed it yet. I've got a surface or a solid and a pin that's supposed to fit in there. And that's a perfectly smooth curve. Now I start meshing this and I get this. You can already see there's a bit of overlap, and let's just zoom a bit closer there and you see there's, well, there's not even overlap, there's a gap, but there's an overlap. And the reason for that is it's because we've got a discretized mesh of that perfectly smooth curve. So if I fit a curve through there, it will exactly look like the original circular section, in other words, that section over there. But I don't have nodes, the same number of nodes on the two, and even if I had it, it may have been rotated a bit so that some places it overlaps and some it doesn't. Some there's an interference. So the solution to this would in theory be to mesh finer. Now, that doesn't work that well. If I try to do it, I'll see my overlaps reduce. It's not such large overlaps anymore, and I don't have such large gaps, but the problem doesn't disappear. Bear in mind that a couple of microns interference fit can cause really severe stresses. Some interference fits are of the order of 10 microns. So 10 micron error in overlap or gap will cause utterly wrong answers. So the alternative, and that's what Marc has implemented, is to define what it calls a smoothed contact body. So in other words, it fits a spline through all of these outside edges or faces, depending on whether it's a planar or a three-dimensional analysis. If I fit the spline through these, the red meshes nodes, it'll be very close to a perfect circle. If I then make contact from the blue one's nodes to the spline instead of these faces, that spline will run through there and perfectly touch there, go through this node and so on. So that means if the red part is the smooth one and I make contact from the inside to the outside, it will make perfect contact without generating any weird stresses anywhere in the model. I could have done the reverse as well and made the inside one the spline or the smooth body. So then the outside can make contact to this. I know there's some slight complications. It's really easy to get past those. It has to do with, if I just go back to this, what happens with the spline through a corner there. Spline says it has to be smooth. So what we'll see is a nice straight line there, and there at the end it does something funny and then it goes smooth again. To fix that, we simply need to specify this is discontinuity, meaning it'll fit one spline through there and a separate one through there, separate one through that section. Okay, so this is a very convenient way to, even with a pretty coarse mesh, still get really good answers. Another advantage of this is it fits the spline every iteration. So in other words, if I load this hole will become oval. It'll separate there. And initially it will make contact just at the bottom, but then it will grow larger and larger, the area that's making contact. And that spline will now follow that new displaced shape. So it keeps on representing that contact region pretty well. So we typically use this whenever we have anything that's curved touching anything else that's curved. That's the one case. And the other one is, even if you've got a flat part touching a flat part, as long as due to the deformation, one of those may become curved, you can also still use this. It will improve the results. In those cases, just not as needed as it is for something like this, which started out as a pretty smooth, or intended to be as a pretty smooth curve. Now, just a side note, second order elements has got a similar behavior. Because if I add that mid node, that becomes a parabola, not a circle. So it's better than it was, at least it's not straight lines, but it's still not perfect. So the next is in terms of contact parameters. And when I talk about contact parameters, I'm not talking about settings. I'm talking about values that you can change that changes something in how the contact behaves. So the first one is the distance tolerance or the contact tolerance. Now the default is based on the mesh size. The finer the mesh, the smaller that number will be. Now this dashed section there is the inside of the part. So this is the solid, and there where there's no dashes, that's the air. And that distance tolerance, there's a second parameter that influences this. But if that parameter was 0, it means whatever the distance tolerance or contact tolerance is on the outside, the same on the inside. So the total checking region is that twice the tolerance. In other words, a node starting there moves closer, 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 closer. Nothing happens, nothing happens. It crosses that line. It's now inside the checking region, inside the tolerance. Then it gets pulled to the surface. The reason for that is the assumption that it should probably have been in contact. So that's why it's trying to pull it to the surface. I'm not saying it's necessarily a good idea. It depends on the model. Some models it should have been, others not. Okay, so if a node is there, it will be pulled to the surface. At that point, if it does the iteration and it realizes there's a tensile force, it will release it again. However, if it's a compressive force, it will then stay in contact. Same goes if a node moves from there to the inside there, it's still inside that checking region, so it will be pushed back onto the surface and it will get stuck there. And again, it will do the same iterations afterwards to see whether it should stay in contact or not. Now, as you can imagine, it's pretty important to choose a reasonable tolerance because if it moves from there to there, it must contact completely. Now, it's something that doesn't often happen. It's very seldom actually that we see it. But still, if you start messing around with a tolerance, you typically get that kind of behavior. If you make it very small, for example. The second parameter is called the bias. The default value is 0.95. So the purpose of the bias is take this checking region, which this is a bias of 0, meaning the same tolerance outside as inside, and that total distance still stays twice the tolerance, but it moves it into the body. So this is 0. This is probably about, let's say, 0.7 or something. If it was exactly 1, that outside face would, or the outside region would perfectly lie on top of that face. So the default says 5%. If we look at that equation, 1 minus 0.95, it's 5% of the tolerance is outside and 1.95 will be on the inside. Okay, so in other words, the distance tolerance changes that size and the bias changes where it occurs. Okay, so here's an example of what typically goes wrong. Now, this is one of the reasons why we can't just take a model, say, make everything contact bodies, magically run it, and it works perfectly. So I've got two parts which seem to be touching, but I zoom in over there and I say, there's some gap. Now, I'm just using a value of 1 to make the numbers a bit easier to understand. It could have been smaller, it could have been larger, but this is typically that node is not supposed to be in contact because there's a gap. But what if there was a CAD modeling error? That's something you see a lot where the person doing the CAD modeling is maybe a bit lazy and didn't clean up all this perfectly. In some cases, doesn't even matter in reality because when you assemble it, will still be okay. But from the finite element perspective, I can't apply a load there initially because there's a gap. There's no link between this one and this one initially. So I need some way to try and clean up this gap initially. So I've got a 1 millimeter gap and I start messing around with the distance tolerance. Initially, I ran it without changing it and I saw these are not in contact. So let's try again. Let's start changing the distance tolerance. I make it 1 millimeter, but it doesn't work. So I go, okay, wait a minute. If that is 1 millimeter, round of error would mean that node may be just outside of 1 millimeter. I mean, 1 micron more is, well, more than 1 millimeter. So let's just make it 1.1. So then definitely it should be in, and it doesn't work. I make it 5 millimeter, and it doesn't work. I make it 19 millimeters and it still doesn't work. I make it 21 and then suddenly it works. And hopefully by this time it should be obvious that's the gap, but this is the value that I specify why something is wrong. Okay, so we run the model, we see that's in contact, but the model takes extremely long per iteration and the results are just weird. So what happened? So this is what happened. What's the default bias? It's 0.95. If I use that equation for that outside region, it says 1 minus 0.95, which is 0.05 times my tolerance, is that checking region on the outside. So if I use a 1 millimeter, it only means 0.05 millimeter on the outside and 1.95 on the inside. So that's why it doesn't work. 20 millimeters means 1 millimeter outside and 39 on the inside. Now, getting back to this previous slide, that's why I used 19 and 21 and not 20. The reason for that is, again, that argument about if it's exactly 20, it's 1 millimeter. So if that node is exactly 1 millimeter away, a round of error may be enough to say just outside of 20, outside of that 1 millimeter. So that's why this will definitely work. 1.05, it's fine. So this is not a good way to do it. If I change the bias to 0.01, and I'll explain later why not 0, but let's make it 0.01. If I then plug it in, my checking on the outside is 0.99, so it's 1 minus 0.01, which is 0.99 times my tolerance. So if I now make it 1, I'll get 0.99 on the outside, which is obviously too small. So let's make it slightly larger, 5 or 10%, and I get that on the outside. Great, this works. So this is this is the tolerance I need if I reduce my bias to well, more reasonable value for this specific problem. Okay, so I run the analysis. It runs a lot faster than the previous one where I made the tolerance 22 millimeters, and the contact results make sense. Why the previous model? If I use this 21 millimeter without a bias, why does it run so long? Because now it needs to check a lot more nodes and faces, and it may even get stuck to the wrong face because a face somewhere over there may be within 21 millimeters, so it's stuck to the wrong face. Or if it's a plate shell element, in other words, it may get stuck to the wrong side of that shell element. And because it needs so many more checks, it's taking a lot longer, but at the same time, it gives bad answers simply because it gets stuck to the wrong location. So changing this bias in this case moved only the nodes that was in that region closer instead of getting stuck to the wrong face. That's why runtime was fast. We didn't need to check excessive numbers of elements and nodes and stuff. And we look at the contact results and it makes sense. Okay, so this is the right way to do it. You're not allowed to ever separate distance tolerance and bias from each other. They always go together. Once we start looking at the contact table, you'll see that it's something that you can specify per body pair, but there's also a global setting that says if you haven't changed it in the contact table, use the default value. And as I say, the default is 0.95. Now, why did I specify 0.01 instead of 0? And the problem is, I'm not certain whether it's still an issue, but initially in the Marc deck, if you write a value of 0, Marc interpreted it as use default. Okay, so that was a convenient way and a elegant way, at least initially, but it complicates things now later on. So if you make it just some small value, 0.01, 0.0001, doesn't matter. Anything that's not exactly 0 should work. Just be careful of using exactly 0 because you may get this kind of surprise where it's using that, but you think it's 0. Okay, and then on to the last section I want to talk about is contact and separation conditions and so on. So what the algorithm needs to do. So whenever a node penetrates in an iteration, so initially, let's say a node was not in contact, now it penetrates, so it's inside some element. So what Marc needs to do, or Nastran need to do, is it need to move that, in other words, project it normal to the face back to the element. Then we need to add contact equations. How that exactly looks like depends on the solver. Marc uses for node to segment MPC kind of an equations. For segment to segment, it's a penalty kind of a method, Lagrangian multipliers and so on. Most finite element codes have got their own way of implementing how these contact equations look like. Okay, but either way, we move it to the surface, we add the equation, but then we need to redo the iterations. Or at least that iteration to see if it is converged. So that's if a node comes into contact. But what if it generates a tensile force or stress. And again, you'll notice there's a comment there. If it's a tensile force, then it should release. A node you're trying to pull it away from the other surface, which means it should release these contact equations. It doesn't need to move the node because we'll redo the iterations. So based on that release of the equations, that node will in any case move further away usually. If for whatever reason it comes into contact again, it'll just add the contact equations again. The reason that may occur is simply because a lot of nodes, argument's sake, was separated, but only a few should have been based on the previous contact state. This contact state is simply meaning which node was in contact. Okay, now the reason I say stress is I can use either force or a stress-based method for first order elements, but for second order elements, forces does not work. And the reason it doesn't work is we've got a really weird force distribution for a constant stress state. In some cases, some element types, T10 is a good example, we actually have a tensile force at the corner nodes and a massive compressive force in the mid nodes, but it perfectly represents a, well, constant stress state, compressive stress state. So in other words, we can't use forces because if I release that node on the corner which says there's a tensile force, it'll actually push through. There's nothing the solver can do about that other than trying to find an element formulation which doesn't have that issue. But we're using some kind of a parabolic interpolation, which means it's impossible to find something that works perfectly only on forces. So in other words, we can use either forces, which is the default, but forces or stresses for first order elements. In other words, a tensile force, tensile stress. But for second order elements, we have to use stress. Okay, so in Marc, if you used Marc before, the moment you have second order elements in a contact body, it'll automatically switch to this and leave and gray out this section. For Nastran, it depends on the preprocessor you use, whether or not it may still actually suggest forces, even if they're second order elements. Just a side comment there. Okay, and then the last one for the day is what is glued contact? Okay, so touching contact is typically what we think of as contact. It makes contact or it doesn't. If I try to lift it up, it releases. Now, glued contact says we use the same algorithms, but we change two things in that contact algorithm. The first is we allow tensile and compressive loads. In other words, if it started in contact and I apply tensile load, it will not separate and there's infinite friction. So that thing, in other words, is stuck in place on that other face. So in other words, it's the equivalent of welding parts together. Or, well, if we look at what it's typically used for, we connect the similar meshes. So in other words, I can have a first order and a second order set of elements in my mesh, and I can connect it to first and second order elements cannot be connected at nodes unless you really likes either wrong or bad answers. The contact method will allow much better transition from the first to the second order elements than simply trying to merge nodes. Okay, so that's one possibility. Why would I want to do this? Let's say I've got a large part that's in general not that complex, easy to X mesh, for example. I can use a coarse mesh, it works fine. But I've got a region that I need very fine and more accurate results. So I can cut out the section, mesh that argument sake with either second order or much finer elements, and I can glue this into the first one. So this method is typically for a single part. So we can do this, find the coarse mesh transition, but we can also use it because two parts are really either welded or glued together. So by doing this, I do not have to have a continuous mesh where I can need to or can merge nodes. I can simply glue the two together. In terms of nonlinearity, glued contact is either linear or very close to linear. It simply says connect the nodes initially, and then there's certain contact equations that need to be applied. I say nearly linearly. If there's large rotations on the model, the contact equations may differ a little bit. But apart from that, it's very close to linear. If I look at contact on the other end, in other words, touching contact that can separate, that's one of the most nonlinear effects that we can typically see in a model. So if I look at, as an example, plasticity as being nonlinear, I've got an elastic slope, but the moment it goes plastic, I just go either on a different slope or the slope that slowly curves to a lower stiffness or effective stiffness. Contact is not that forgiving. It simply says there's zero stiffness between two parts if they don't touch, and there's infinite stiffness at that touching location between the two parts the moment they touch. And the only thing that we typically see that's even more nonlinear is friction, because initially it's stuck in place, the sticking condition. Then we need to load it until it exceeds the normal force times the friction coefficient, static friction coefficient in this case. The moment it exceeds that, it then takes away the constraint, which effectively was an infinite stiffness sideways, and it replaces it with a force, and that force is now simply normal force multiplied by the friction coefficient, the dynamic or kinematic friction coefficient in this case, and the direction of that is simply opposite to the sliding direction. So in this case, we start with an infinite friction or infinite stiffness sideways relative to between the two parts, and we transition to a force, and there's some discontinuity in between as well. So that's for the stick slip method. Now, at some point, we'll spend a bit more time on friction models, the pros and cons, the reason they exist, and so on. But okay, so that's what I wanted to discuss for today. So just to recap, we spoke about, if I go to the beginning, we spent some time on the contact algorithms, in other words, why we need them, the ability to connect the similar meshes, but then we spend time on contact body pairs, sorry, not contact bodies, the different types you get, some setting changes, the distance tolerances and bias, and then the last was what changes during an example contact analysis.